Hello there, and welcome to Earth and Beyond, where curiosity gets cozy, and the cosmos takes the scenic route to slumber. Tonight, we drift towards something that arrived from distances we can barely comprehend, carrying within its frozen heart the chemical memories of a star system we will never visit, an object designated 3I, Atlas, the third confirmed interstellar visitor to grace our solar system with its presence, and perhaps the most enigmatic of them all. The story begins not with drama, but with quiet patience, the kind that defines most genuine discoveries in astronomy, where years of watching and waiting suddenly crystallize into a single moment of recognition that changes everything. Before we step into that July evening, when humanity first glimpsed this cosmic wanderer, let me ask you something simple. Where are you listening from right now? Maybe you're tucked into bed, curtains drawn against the world outside, letting the weight of the day finally slide away from your shoulders as darkness settles around you like a familiar blanket. Maybe you've got the soft glow of a bedside lamp casting gentle shadows across the ceiling, that particular quality of a light that exists only in the hour before sleep, when the mind begins its slow surrender to rest. Or maybe you're somewhere in between, neither fully awake, nor quite ready to let go, suspended in that liminal space where thoughts drift like clouds, and the boundary between consciousness and dream becomes wonderfully blurred. Wherever you are, imagine for a moment looking up at the night sky, not through a telescope, not through any instrument at all, but simply with your eyes, the same eyes that ancient peoples once used to map the heavens, and wonder what moved among the fixed stars. Imagine that somewhere in that vast darkness, invisible to you, something is moving, something that doesn't belong to our sun, that never has, that carries within it evidence of processes and places that exist light years beyond anything human eyes will ever directly see. If you find this kind of gentle exploration into cosmic mystery soothing, I'd be grateful if you gave the video a like, or maybe subscribed. It helps this quiet corner of contemplation reach others, who might also enjoy drifting through the universe's stranger stories this way. Now then, let's move carefully into that remarkable discovery, and the journey that preceded it. The first day of July, 2025. The date itself seems almost arbitrary when you consider the timescales we're about to discuss. But for our purposes, for the human record, this is when everything changed. High in the Chilean Andes, where the air is thin and the stars burn with a clarity that lowland observers can only dream of, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, was doing what it does every clear night, watching, recording, comparing. ATLAS wasn't designed to find interstellar visitors. Its purpose is more immediate, more pressing, in a certain sense, to identify objects that might threaten Earth, rocks from our own solar system that could be on collision courses with our fragile world. But the universe, as it often does, had other plans for this particular telescope on this particular night. The detection itself was unremarkable in its mechanics. A faint streak appeared in the survey images, smudge of light moving against the background stars, in a way that suggested something closer than the distant galaxies and nebulae that fill our telescope's fields of view. Automated systems flagged it, as they flag hundreds of objects every month, and human astronomers, bleary-eyed perhaps, but certainly dedicated beyond what most people would consider reasonable, began the careful work of calculating its trajectory. And that's when the numbers started telling a story that no one expected. The object wasn't on an elliptical orbit. It wasn't bound to our sun, in the gentle gravitational embrace that characterizes everything born within our solar system's ancient disk of gas and dust. Instead, its path was hyperbolic, a mathematical term that carries a profound implication. This object was moving too fast, with too much energy, to be captured by the sun's gravity. It had come from elsewhere, and it would return to elsewhere, passing through our cosmic neighborhood like a stranger on a highway, here briefly, then gone forever into the darkness between stars. But here's what makes this discovery so different from those brief headlines you might have seen about previous interstellar visitors. This object, this wanderer, 3I Atlas, was active. It was producing a coma, that fuzzy cloud of gas and dust that transforms a simple rock into what we call a comet. And that activity, that awakening under our sun's distant warmth, meant something profound. We were watching chemistry unfold, watching volatiles that had been frozen since before our sun was born suddenly respond to heat, releasing molecules and particles that carried within them signatures of the environment where they formed. Think about what that means for a moment, as your breathing perhaps slows, as your body settles deeper into whatever comfortable position you found. This object, this collection of ice and rock, had travelled through the galaxy for an incomprehensible span of time. It had drifted through the cold between stars, where temperatures hover just a few degrees above absolute zero, where the faint light of distant suns provides no warmth whatsoever, where nothing changes, nothing moves in the way we understand movement. It had been, in every meaningful sense, dead, frozen in a state of suspended existence. And then, slowly at first, then with gathering intensity, it began to feel our sun's warmth. But here's where the story takes an intriguing turn, where the careful observations of dedicated astronomers reveal something that challenges our expectations. Because 3I Atlas didn't wait until it was close to the sun to wake up. No, observations that would later be carefully analysed, images pulled from archives and studied with fresh eyes, revealed that this object had begun producing dust and gas much farther out than any typical comet would. 6 astronomical units from the sun. Let that number settle in your mind for a moment. An astronomical unit is the distance from Earth to the Sun, about 93 million miles, or 150 million kilometres, a span so vast that light itself, travelling faster than anything in our experience, takes 8 minutes to cross it, 6 times that distance. That's roughly the orbit of Jupiter, that giant world with storm systems larger than Earth, and a collection of moons that could themselves be planets in any other context. At that distance, the sun's warmth is faint, so faint that you might not even feel it as warmth. If you could somehow stand there in the vacuum, the sunlight is dim, providing only about 1/30th the illumination we receive here on Earth. And yet, despite this, despite the cold that should have kept everything locked in frozen silence, 3I Atlas was already active, already releasing material into space. What substance could cause such dramatic outgassing? So far from warmth? The answer, drawn from careful spectroscopic observations, from the patient analysis of light broken into its component colours, and compared against known chemical signatures, points to molecules that belong to a different category of volatile than the water ice we're most familiar with. Carbon monoxide, perhaps, or carbon dioxide, substances that can sublimate, that can transform directly from solid to gas, at temperatures far lower than water ever requires. This suggests something fascinating about where 3I Atlas formed, about the conditions in its birth system. If its nucleus is rich in these exotic volatiles, these substances that evaporate even in the deep cold beyond Jupiter's orbit, then perhaps it formed in the outer reaches of another star's planetary system, in those frigid zones where sunlight has almost no meaning, where only the coldest, most delicate materials can condense out of the primordial disk that swirls around young stars. Or, perhaps, and this is where speculation becomes especially intriguing, these volatiles accumulated during its journey between stars. Space is not perfectly empty, not perfectly void. Between stars there exist diffuse clouds of gas and dust, regions where molecules form despite the cold, where chemistry proceeds at a glacial pace, but proceeds nonetheless. Could 3I Atlas have spent its journey not in complete isolation, but drifting through these clouds, accumulating a thin veneer of materials that don't exist in our solar system's chemistry, collecting the frost of interstellar space itself? We don't know. And there's something beautiful about that uncertainty, something that makes the mind wander in pleasant ways as sleep approaches, considering possibilities that no one can prove or disprove, questions that might never be fully answered, yet remain endlessly fascinating, in their ambiguity. As the summer of 2025 progressed, Earth continued its steady orbit around the Sun, and 3i Atlas continued its hyperbolic plunge toward perihelion, that point of closest approach, where solar heating would reach its maximum intensity. Astronomers around the world turned their instruments toward this visitor. The James Webb Space Telescope, humanity's most powerful infrared eye on the universe, captured spectra revealing chemical compositions. Ground-based observatories in Chile, Hawaii, and the Canary Islands monitored brightness changes and the evolution of the coma. Radio telescopes listened for molecular emissions that optical instruments could not detect, and slowly, through the accumulation of data points, spectral lines, and careful measurements, a picture began to emerge. Not a complete picture, not a finished portrait, but a sketch, with fascinating details and equally fascinating gaps. The object appeared to be rotating, spinning on its axis roughly once every 16 hours. Not the chaotic tumbling of a shattered fragment, but a relatively stable rotation that hinted at either a uniform mass distribution or perhaps some hidden history, a past collision or gravitational encounter that had left it spinning in this particular way. Its brightness varied, but not dramatically. The light curve, the graph showing how bright the object appears over time, was relatively flat compared to other interstellar visitors. That suggested either a nearly spherical shape, or perhaps a surface composition that reflected light uniformly, regardless of which face was turned toward our instruments. This uniformity was itself puzzling, because most comets in our solar system show significant variations as they rotate, with patches of ice or regions darkened by accumulated dust. But perhaps the most striking observation, the one that would generate the most discussion and the most puzzled frowns among astronomers, was the emergence of what came to be called the anti-tail. Imagine, if you will, a comet's typical appearance. You've probably seen the pictures, those spectacular images of bright nuclei trailing long, elegant tails of dust and gas. Tails that always point away from the sun, pushed outward by solar radiation and the solar wind. It's one of the most reliable phenomena in all of astronomy, a fact that seems inviolable, a law of basic physics without exception. Except 3i Atlas seemed to be developing a tail that pointed the wrong way, not entirely toward the sun. That would be impossible. It would break the very principles of motion and light, but rather, observations captured by patient astronomers revealed structures in the coma that extended sunward, that seemed to defy the expected direction, creating a fan-shaped pattern that pointed back along the comet's trajectory toward our star. The explanation, when it finally emerged from careful modelling and analysis, revealed something elegant about the physics of ice, sunlight, and the peculiar geometry of 3i Atlas's passage. The antitail wasn't actually moving toward the sun in defiance of radiation pressure. Rather, it represented a region where ice particles could survive longer, where the angle of solar illumination created conditions that allowed water ice grains, perhaps mixed with other volatiles, to persist at greater distances from the nucleus than in other directions. Picture it this way, as your thoughts perhaps begin to blur and drift. The comet is ejecting material in all directions, as any sublimating ice would, but in the direction of the sun, the grains experience maximum heating, maximum sublimation, and their survival time is extended just enough, the physics balance just precisely enough, that they can travel farther before disappearing than grains moving in other directions. The result is an asymmetric coma, a tail that isn't really a tail in the traditional sense, but rather a map of where ice can exist around this object, a visualization of the boundary between solid and gas, between matter and absence. It's the kind of phenomenon that makes you appreciate the complexity hidden within what seems simple. The way a comet, that archetype of celestial objects that humans have observed and feared and wondered at for millennia, can still surprise us, can still reveal behavior that requires new thinking, new models, new appreciation for how subtle physics can produce dramatic effects. If you find this sort of calm exploration pleasant, I'd be grateful if you gave the video a like, or maybe subscribed. It helps this little space reach others who might also enjoy wandering through cosmic mysteries this way. It's a small gesture, but it helps more than it looks. I'm not asking because numbers matter here, not in the way they do in most places. I'm asking because the more people who join in, the richer these quiet conversations become. Sometimes, it's the smallest comment from someone in a completely different part of the world that changes how you think about something, that adds a perspective you hadn't considered, that reminds you how vast and varied human experience can be, even as we all look up at the same sky. Now, as July turned to August, and August began its slow fade towards September, 3i Atlas continued its journey inward, continued its transformation from dormant wanderer to active comet, though an unusual one, a strange one that would keep astronomers puzzled and fascinated in equal measure. The brightness increased, but not smoothly. There were variations, jumps and fluctuations that hinted at discrete events, perhaps fresh ice being exposed as surface layers sublimated away, or internal pressures building and releasing as warmth penetrated deeper into the nucleus. Each night's observations added another data point to the growing archive, another piece to a puzzle that was becoming more complex, rather than less, as more information arrived. And through it all, moving at speeds that dwarf anything we experience in our daily lives, 3i Atlas drew closer to its perihelion date, that moment in late October, when it would pass closest to the Sun, and solar heating would reach its maximum intensity. What would happen then? Would the anti-tail persist? Would new chemical signatures emerge as even more deeply buried volatiles began to sublimate? Would the nucleus fragment under thermal stress, breaking apart to reveal pristine interior materials that had never felt any sun's warmth? These questions hung in the astronomical community, generating emails, conference calls, hurried papers submitted to journals, all trying to predict, to model, to understand what might occur when this visitor from beyond finally experienced the full force of stellar radiation from a star that wasn't its parent, from an environment utterly alien compared to wherever it had formed. But for now, for this moment, as you lie in darkness listening to these words, perhaps with your eyes closed, perhaps with your breathing already taking on that slower rhythm that precedes sleep, the important thing isn't the answers. The important thing is the presence of this object. This confirmation that our solar system isn't isolated, that we exist within a galaxy where things move between stars, where the spaces we call empty are actually highways for ancient ice, carrying the chemistry of distant places. 3i Atlas arrived bearing no messages in any language we would recognize, carrying no artifacts or signals that would suggest intelligence or intent. But it carried something perhaps more profound, evidence of processes occurring throughout our galaxy, proof that stellar systems exchange materials over vast timescales, that the chemistry happening around other suns finds its way eventually to our neighborhood, that we participate in a cosmic ecosystem of matter and energy, operating on scales beyond human comprehension, yet still real, still present, still worthy of our attention and our wonder. The first section of this journey has brought us from discovery to recognition, from that initial detection on a July evening to the growing understanding of what 3i Atlas represented. A visitor from beyond, awakening under our sun's warmth, displaying behaviours both familiar and strange, challenging our models, while confirming our deeper understanding of how comets work, how ice responds to heat, and how the universe orchestrates these remarkable exchanges between systems separated by distances that light itself requires years to cross. As we pause here, as this first chapter draws to its gentle close, let that image rest in your mind. A small object, perhaps a few kilometers across, perhaps less, carrying within its frozen structure the accumulated history of its formation and journey. Now, illuminated by our sun, now visible to our instruments, transformed from an invisible wanderer into an observed phenomenon, from a hypothetical possibility into a confirmed reality. The night is deep, your breathing is slow, and somewhere out in the darkness beyond our atmosphere, beyond the moon's pale light and the planet's steady glow, 3i Atlas continues its passage, indifferent to observation, unconcerned with our wonder, simply being what it is. Ice and rock, chemistry forged around another star, now passing through our corner of the galaxy, like a message in a bottle, thrown into an ocean so vast that its currents move on timescales making human civilizations seem like brief flickers of awareness. Rest now. The comet will still be there in the morning, continuing its journey, and tomorrow's observations will add new details to the story, new questions to the growing collection of mysteries that make astronomy not just a science, but a practice of wonder, where the more we learn, the more we realize how much remains unknown, how many possibilities live in the vast darkness between what we can observe and what we can imagine. We have drifted together through the discovery, through those first remarkable observations that revealed 3i Atlas as something genuinely alien to our solar system. Now, as you settle perhaps even deeper into rest, as the boundaries between waking thought and sleeping dream become increasingly porous and undefined, we turn our attention to something more subtle, more profound in its implications, the chemistry this visitor carried with it. Chemistry, you see, is biography. Every atom in existence was forged in stellar furnaces or in the violent deaths of stars, and the way those atoms combine, the molecules they form, the ratios in which they appear, all of this tells a story about where they've been, what temperatures they've endured, what pressures shaped them. When we analyse the light reflected or emitted from a comet like 3i Atlas, we're not just measuring wavelengths and intensities. We're reading a chemical autobiography written over billions of years, and this particular autobiography contains passages that shouldn't exist, elements appearing in ratios that violate our understanding of how things ought to be, if ought even has meaning, when describing an object that formed light years away, under conditions we can only imagine. Let your breathing find its own rhythm now, slow and steady, as we explore what might be the most peculiar aspect of this already peculiar visitor. Because while the anti-tale was strange, while the early activity raised questions, the chemical signatures emerging from spectroscopic observations revealed something that challenged not only our models of comets, but our very understanding of planetary formation itself. And through it all, moving at speeds that dwarf anything we experience in our daily lives, 3i Atlas drew closer to its perihelion date, that moment in late October, when it would pass closest to the Sun, and solar heating would reach its maximum intensity. What would happen then? Would the anti-tale persist? Would new chemical signatures emerge, as even more deeply buried volatiles began to sublimate? Would the nucleus fragment under thermal stress, breaking apart to reveal pristine interior materials that had never felt any sun's warmth? These questions hung in the astronomical community, generating emails, conference calls, hurried papers submitted to journals, all trying to predict, to model, to understand what might occur when this visitor from beyond finally experienced the full force of stellar radiation from a star that wasn't its parent, from an environment utterly alien compared to wherever it had formed. But for now, for this moment, as you lie in darkness listening to these words, perhaps with your eyes closed, perhaps with your breathing already taking on that slower rhythm that precedes sleep. The important thing isn't the answers. The important thing is the presence of this object, this confirmation that our solar system isn't isolated, that we exist within a galaxy where things move between stars, where the spaces we call empty are actually highways for ancient ice, carrying the chemistry of distant places. 3i Atlas arrived bearing no messages in any language we would recognize, carrying no artifacts or signals that would suggest intelligence or intent, but it carried something perhaps more profound, evidence of processes occurring throughout our galaxy, proof that stellar systems exchange materials over vast timescales, that the chemistry happening around other suns finds its way eventually to our neighborhood, that we participate in a cosmic ecosystem of matter and energy, operating on scales beyond human comprehension, yet still real, still present, still worthy of our attention and our wonder. The first section of this journey has brought us from discovery to recognition, from that initial detection on a July evening to the growing understanding of what 3i Atlas represented, a visitor from beyond, awakening under our sun's warmth, displaying behaviours both familiar and strange, challenging our models, while confirming our deeper understanding of how comets work, how ice responds to heat, and how the universe orchestrates these remarkable exchanges between systems separated by distances that light itself requires years to cross. As we pause here, as this first chapter draws to its gentle close, let that image rest in your mind. A small object, perhaps a few kilometres across, perhaps less, carrying within its frozen structure the accumulated history of its formation and journey. Now, illuminated by our sun, now visible to our instruments, transformed from an invisible wanderer into an observed phenomenon, from a hypothetical possibility into a confirmed reality. The night is deep, your breathing is slow, and somewhere out in the darkness beyond our atmosphere, beyond the moon's pale light and the planet's steady glow, 3i Atlas continues its passage, indifferent to observation, unconcerned with our wonder, simply being what it is. Ice and rock, chemistry forged around another star, now passing through our corner of the galaxy, like a message in a bottle, thrown into an ocean so vast that its currents move on timescales making human civilizations seem like brief flickers of awareness. Rest now. The comet will still be there in the morning, continuing its journey, and tomorrow's observations will add new details to the story, new questions to the growing collection of mysteries that make astronomy not just a science, but a practice of wonder, where the more we learn, the more we realize how much remains unknown, how many possibilities live in the vast darkness between what we can observe and what we can imagine. We have drifted together through the discovery, through those first remarkable observations that revealed 3i Atlas as something genuinely alien to our solar system. Now, as you settle perhaps even deeper into rest, as the boundaries between waking thought and sleeping dream become increasingly porous and undefined, we turn our attention to something more subtle, more profound in its implications, the chemistry this visitor carried with it. Chemistry, you see, is biography. Every atom in existence was forged in stellar furnaces or in the violent deaths of stars, and the way those atoms combine, the molecules they form, the ratios in which they appear, all of this tells a story about where they've been, what temperatures they've endured, what pressures shaped them. When we analyse the light reflected or emitted from a comet like 3i Atlas, we're not just measuring wavelengths and intensities, we're reading a chemical autobiography written over billions of years, and this particular autobiography contains passages that shouldn't exist, elements appearing in ratios that violate our understanding of how things ought to be, if ought even has meaning, when describing an object that formed light years away, under conditions we can only imagine. Let your breathing find its own rhythm now, slow and steady, as we explore what might be the most peculiar aspect of this already peculiar visitor. Because while the ante-tale was strange, while the early activity raised questions, the chemical signatures emerging from spectroscopic observations revealed something that challenged not only our models of comets, but our very understanding of planetary formation itself. In late August, as 3i Atlas continued its approach toward the Sun, now inside the orbit of Mars, heating steadily under increasing solar radiation, a team of astronomers using the Very Large Telescope in Chile, that magnificent array of instruments perched high in the Atacama Desert, where the air is so dry that water vapour barely exists, pointed their spectroscope toward this interstellar visitor. They were looking for the usual suspects, the molecular signatures that any comet might display, water vapour, that most fundamental volatile whose sublimation drives cometary activity, carbon monoxide, carbon dioxide, those simple carbon compounds found throughout the universe, perhaps even some organic molecules, those carbon-based structures that form so readily in cold, dark places where chemistry proceeds at a glacial pace, but proceeds nonetheless. What they found included those expected signatures, but it also included something that made them check their calibrations, run their analysis software again and again, and exchange increasingly puzzled messages with colleagues around the world. Nickel, atomic nickel, glowing with its characteristic green emission lines, present in abundances that simply shouldn't make sense, given what else they were observing. Now, finding metals in cometary atmospheres isn't unprecedented. Comets within our own solar system sometimes show traces of iron and nickel, atoms somehow liberated from the rocky minerals that make up every comet's nucleus. The mystery has always been how these atoms enter the gas phase, how they become free to emit light, given that the temperatures required to vaporize rock are far higher than what any comet experiences, even near the Sun. But 3I Atlas wasn't just showing nickel, it was showing nickel in extreme abundance, relative to iron, where solar system comets typically display a nickel to iron ratio about 10 times higher than the solar average. 3I Atlas showed ratios even more extreme, ratios suggesting either a formation environment radically different from anything we know, or some process during its interstellar journey that enriched its surface in nickel, while depleting iron. Think about what that means, as your mind perhaps begins to wander, in those pleasant, unfocused ways that precede sleep. Somewhere out there, orbiting a star we cannot identify, in a planetary system whose architecture we will never know, conditions existed that allowed this particular ratio of elements to be incorporated into the materials that eventually became 3I Atlas. Was it a system richer in nickel to begin with? Did it form in a region touched by the ejecta of a supernova, one of those explosive deaths of massive stars that seed galaxies with heavy elements, depositing more nickel than our own stellar neighbourhood ever received? Or perhaps, and this is where the analysis becomes truly intriguing, the answer lies not in where it formed, but in how these atoms are being released into the coma. As astronomers studied the radial distribution of nickel emission, measuring how the intensity changed with distance from the nucleus, they discovered something elegant. The nickel appeared concentrated close to the nucleus, far more so than the cyanogen emissions also visible in the spectrum. The characteristic E-folding distance, that radius where intensity drops to about 37% of its maximum, was remarkably small for nickel, just a few thousand kilometers, compared to much larger distances for other species. This concentration near the nucleus suggested that whatever was producing the nickel atoms was short-lived, breaking down rapidly once exposed to sunlight and the harsh vacuum of space. And that observation pointed toward a fascinating possibility. Metal carbonyls. Imagine molecules where metal atoms are bound to carbon monoxide groups, creating fragile structures that can exist only in the cold and dark. Nickel carbonyl, for example, where a single nickel atom is surrounded by 4 carbon monoxide molecules, a compound stable at low temperatures, but one that decomposes instantly when heated or exposed to ultraviolet light. These substances exist in human industry, used for metal refining and chemical processes, but they could also exist naturally, in the frozen outer reaches of planetary systems, in those zones beyond where planets form, where even the most exotic chemistry can survive. If 3I Atlas carried metal carbonyls within its nucleus, then as it approached the Sun and surface temperatures rose, these molecules would sublimate, enter the gas phase, and then rapidly decompose under solar ultraviolet radiation, releasing free metal atoms that could emit their characteristic light before being swept away by the solar wind or reabsorbed into dust grains. This elegant hypothesis would explain both the unusual nickel abundance and its tight concentration near the nucleus. But it would also imply something profound about 3I Atlas's birth environment, that it formed in a system where carbon monoxide was abundant enough and temperatures were low enough for these exotic metal organic compounds to condense out of the primordial gas and become part of growing cometary nuclei. Our own solar system, as far as we can tell, doesn't produce comets rich in metal carbonyls, which means 3i Atlas is giving us a glimpse into chemistry that operates differently, in conditions that don't resemble our own stellar neighbourhood, a revelation of the diversity of chemical environments that must exist throughout the Milky Way. But the nickel mystery, fascinating as it was, represented only one aspect of 3i Atlas's strange chemistry. Because as summer faded toward autumn, and the comet drew ever closer to its October perihelion, other observations revealed still more surprises hidden within its spectrum. The James Webb Uzai Telescope, that remarkable instrument orbiting Earth at the second Lagrange point, where gravitational forces balance perfectly and allow stable observation positions, turned its infrared eyes toward 3i Atlas in early August. The James Webb Uzai Telescope sees in wavelengths invisible to human eyes, in the infrared regions where heat glows and where molecules vibrate and rotate in ways that create characteristic absorption and emission features. What the James Webb Uzai Telescope detected was a massive outpouring of carbon dioxide. Not unusual in itself, perhaps. Carbon dioxide is common in comets, a volatile that sublimates more readily than water ice and often drives early activity as comets approach the Sun. But the quantity, the sheer production rate that the telescope's sensitive instruments measured, exceeded predictions by factors that made the data look like errors at first glance. The models had suggested, based on 3i Atlas's observed brightness and the amount of dust in its coma, the carbon dioxide production should follow certain patterns, certain rates that reflected the balance between solar heating and ice sublimation. But the actual measurements showed production rates nearly 2 orders of magnitude higher than these models predicted. 2 orders of magnitude, 100 times more carbon dioxide than ought to be there, given what else we were seeing. Not just a discrepancy, not just an error in the models that could be fixed by changing assumptions about surface composition or thermal properties. This was a fundamental mismatch, suggesting something about 3i Atlas's internal structure or composition was radically different from what we had assumed. Perhaps the nucleus was unusually rich in carbon dioxide ice, containing deposits of nearly pure carbon dioxide, buried beneath a thin crust of darker, less volatile material. As solar heating penetrated this crust and reached these deposits, they would begin to sublimate vigorously, creating internal pressures that could crack the crust and allow gas to escape in sudden bursts rather than gradual diffusion. Or perhaps the structure itself was different, more porous, more loosely consolidated than the dense, compacted nuclei of solar system comets. A rubble pile structure, with voids and cavities throughout, would allow heat to penetrate more rapidly and reach buried volatiles more easily, driving higher production rates than a solid monolithic nucleus would permit. We do not know, not with certainty, not in the way that allows us to close the book and move on to the next question. And there is something almost meditative about sitting with that uncertainty, letting it exist, without demanding resolution, allowing the question itself to be enough for now. As your thoughts drift, as the narrative of 3i Atlas becomes less a sequence of facts, and more a collection of impressions and possibilities, consider what else was found in those careful spectroscopic observations. Radio telescopes, including the James Clerk Maxwell Telescope in Hawaii, detected hydrogen cyanide. Hydrogen cyanide, a simple molecule of 1 hydrogen, 1 carbon, and 1 nitrogen, but one that carries particular significance for astrochemistry, because it is a precursor to more complex organic molecules, to the chemistry that might, under the right conditions, lead towards something we would recognize as biology. The detection itself was strong, unambiguous, a clear signal rising above the noise, at exactly the expected frequency for hydrogen cyanide rotational transitions, and the production rate, calculated from the signal strength, and the known physics of how hydrogen cyanide emits radio waves, suggested abundances similar to what we see in solar system comets, in this respect at least. 3i Atlas seemed familiar, seemed to be operating according to chemistry we understood. But taken together, these observations painted a picture of an object whose chemistry was simultaneously familiar and alien. Familiar, because it contained the same basic building blocks we see everywhere in space: water, carbon dioxide, carbon monoxide, hydrogen cyanide, and organic molecules of various complexities. Alien, in the ratios, in the abundances, in the way these substances were distributed within the nucleus, and released into the coma. Every comet is unique, of course, even within our solar system. No two comets show identical compositions. They formed at different distances from the Sun, at different times in solar system history, from materials that had different thermal and chemical processing histories, but they all share certain commonalities, certain family resemblances that mark them as products of the same stellar environment, the same planetary formation process. 3I Atlas, despite its cometary behaviour, despite displaying the fundamental physics of ice sublimation and dust production that define what we mean by comet, carried within it a chemical signature that marked it unmistakably as an outsider. Not just from another star system, but from a system where chemistry itself operated differently, where the ratios of elements and the types of molecules that formed reflected conditions that simply do not exist in our own cosmic neighbourhood. As August turned to September, and the comet continued brightening, continued its approach toward that fateful perihelion encounter, one more chemical peculiarity revealed itself in the careful observations of dedicated astronomers around the world. Cyanogen, the cyanogen radical, that fragment of larger organic molecules that glows with a characteristic violet colour in cometary atmospheres, showed an extended distribution around the nucleus. Unlike the tightly concentrated nickel emission, cyanogens spread across larger distances, creating a diffuse cloud that suggested longer survival times, before being destroyed by solar ultraviolet radiation or incorporated into dust grains. The radial profile of this emission, the way intensity decreased with distance from the nucleus, could be modelled using relatively simple physics. Molecules were released at some initial velocity by sublimation processes, then gradually destroyed or ionized as they travelled outward through the increasingly harsh radiation environment. The scale length of this distribution, measured in tens of thousands of kilometres, spoke to the balance between production and destruction rates, between creation and dissolution. But what made this observation particularly interesting was the comparison with the nickel distribution. Both species were clearly coming from the nucleus. Both were being released by whatever processes were driving the comet's activity, and yet they showed radically different spatial distributions, suggesting either different parent molecules breaking down at different rates, or different production mechanisms, operating on different timescales. The leading hypothesis, emerging from careful analysis of multiple observations across different wavelengths and dates, suggested that cyanogen was produced primarily from larger organic molecules, perhaps polymers or complex hydrocarbons embedded in dust grains that gradually broke down in the solar radiation field. Nickel, by contrast, came from those exotic metal carbonyls we discussed earlier, molecules that decomposed almost immediately upon exposure to sunlight. Two different chemical pathways, two different timescales, both operating simultaneously in the coma of this visitor from beyond, creating layers of complexity that would take years of analysis to fully untangle and understand. If you're still awake, still following these gentle explorations into cosmic chemistry, you might be wondering what all of this means, what larger conclusions we can draw from these chemical signatures and unusual abundances, and the answer, both satisfying and frustratingly incomplete, is that we are learning about diversity. The universe is vast beyond comprehension, containing hundreds of billions of galaxies, each containing hundreds of billions of stars, many of which host planetary systems where comets form in the cold outer regions. The chemistry occurring in those distant systems reflects the particular history of each star, the composition of the molecular cloud from which it formed, the types of supernovae that enrich that cloud with heavy elements, the dynamics of planetary formation that determined where different materials ended up. 3I Atlas is our third confirmed sample of this diversity, our third opportunity to analyse materials from beyond our solar system, and see how they differ from the familiar objects that share our Sun. And what it is teaching us is that cometary chemistry, despite following the same basic physical principles everywhere, produces different outcomes depending on initial conditions, on formation environments, on the billions of years of processing that occur during interstellar journeys through galactic space. We have wandered now through nickel and carbon dioxide, through hydrogen cyanide and cyanogen, through metal carbonyls and sublimation physics, through questions about formation and evolution, and the processes that create the chemical signatures we observe. The chemistry of 3I Atlas, strange and familiar in equal measure, represents a message written in molecules, a story told through atomic abundances and isotopic ratios, a narrative that stretches back to the birth of its parent star and forward through its journey to our solar system. As this section draws to its close, as we prepare to move forward into other aspects of this remarkable visitor's story, let the chemistry rest in your mind, not as a collection of facts to memorize, but as evidence of something profound, that the universe operates according to the same laws everywhere, but those laws produce infinite variations depending on local conditions. Every stellar system is unique, every planetary formation process creates slightly different outcomes, and every comet carries within its frozen nucleus a record of its particular history, waiting for the warmth of any sun to release those memories into space, where patient observers with sensitive instruments can read them and wonder at what they mean. The night deepens, your breathing slows further, and somewhere in the solar system, 3I Atlas continues releasing its exotic chemistry into the vacuum, continues glowing with the characteristic green of atomic nickel and the violet of cyanogen, continues its journey toward perihelion, where even more of its secrets might be revealed to those watching with telescopes and spectroscopes, and decades of accumulated knowledge about how to read the language of light. Rest now, knowing that chemistry is universal, that the same elements exist everywhere, but the ways they combine and the ratios in which they appear create endless variations on fundamental themes, each one telling a story about somewhere we cannot visit, about processes we can only infer, about the magnificent diversity hidden within what seems, at first glance, to be the simple physics of ice warming under a distant sun. We have explored chemistry, those molecular signatures that mark 3I Atlas as a carrier of alien processes, as a repository of materials forged under conditions different from anything in our solar system. Now, as you rest in whatever darkness surrounds you, as your consciousness perhaps hovers in that pleasant space between awareness and dream, we turn our attention to something equally profound, but operating at a different scale entirely, the physics of ice and light, and the subtle interplay between matter and radiation that creates the visible structures we call cometary phenomena. Physics, unlike chemistry, deals less with what things are made of, and more with how they behave, how they respond to forces, how they move through space and time, according to rules that operate the same way everywhere in the universe. A grain of ice responds to sunlight, according to principles that do not care whether that ice formed around our sun or around a star we will never know. Gravity pulls with the same patient inevitability, regardless of where an object originated. Light pressure pushes outward from any luminous source, following mathematics that transcends all boundaries of place and time, and yet, despite this universality, despite the fact that the same equations describe motion and heat and sublimation everywhere, 3I Atlas managed to create structures in its coma that initially puzzled observers, structures that seemed at first glance to violate the basic principles every astronomy student learns when studying comets. Let your mind drift back to late July, to those early observations, when 3I Atlas was still relatively far from the Sun, still in the early stages of its transformation, from dormant iceberg to active comet. Astronomers looking at high-resolution images noticed something curious about the distribution of material around the nucleus. Instead of the symmetric coma that simple sublimation physics would predict, instead of a roughly spherical cloud of gas and dust expanding outward in all directions from the warming surface, the images showed an asymmetry, a pronounced elongation in a direction that should not make sense, given what we know about how radiation pressure works. There was a fan, a blade-shaped extension of brightness, that pointed not away from the sun, as every tail must point, but toward it. An anti-tail, as we mentioned briefly in our first section, but one that deserves deeper exploration and more careful consideration of what physics could produce such an apparently impossible structure. The key to understanding what was happening lies not in exotic new physics, not in violations of established principles, but rather in the careful consideration of a single factor that often gets simplified away in introductory explanations: the survival time of ice grains. Imagine, if you will, a single particle of water ice ejected from the nucleus of 3I Atlas. Perhaps it's released by the sublimation of carbon monoxide ice beneath it, launched gently into space at velocities measured in meters per second rather than kilometers, drifting away from the surface that gave it birth, with all the urgency of a feather falling in still air. This grain, perhaps 1/10 of a millimeter across, begins its brief existence in the vacuum, immediately absorbing sunlight, and here is where the physics becomes interesting, where the angle matters, where geometry determines fate. If this grain is moving away from the sun, escaping into the anti-solar direction, the face it presents to the sun receives radiation at a particular angle, experiences heating at a particular rate. But if instead this grain is moving sunward, if it happens to be ejected in the direction of our star, then the geometry is different. The illumination angle changes, the rate at which solar energy is absorbed into the ice matrix changes, and consequently, the rate at which that ice sublimates, at which it transforms directly from solid to vapor without passing through a liquid phase, that rate also changes. You might think that moving sunward would mean faster sublimation, that getting closer to the sun would make ice disappear more quickly, and you would be partially right. But here is the subtle part, the detail that makes all the difference. The angle of illumination affects not just how much energy the grain receives, but how that energy is distributed across its surface. A grain moving sunward experiences something called enhanced mass flux in the solar direction. The rate at which molecules leave its sun-facing surface is higher than the rate at which they leave other surfaces. This creates an asymmetric sublimation pattern that actually slows the overall destruction of the grain, that allows it to survive longer, to travel farther from the nucleus before finally disappearing into water vapor and dispersing into the general coma. The result, counterintuitive but mathematically inevitable once you work through the physics carefully, is that ice grains travelling sunward can exist at greater distances from the nucleus than grains travelling in other directions. They carve out what physicists call an anisotropic survival zone, a region where the conditions for solid ice existence extend farther in one direction than in others, and that extended survival zone, filled with ice grains that scatter sunlight and appear bright in our telescopes, creates what looks like a tail pointing toward the sun, not because anything is actually moving toward the sun, in violation of radiation pressure, but because that is where ice can exist at greater distances, where the balance of sublimation and distance creates a visible structure. It is elegant, really, the way physics can produce something that seems impossible, using only the most basic principles of heat transfer and sublimation rates. No exotic explanations required, no new physics needed, just careful attention to geometry and the way illumination angles affect surface processes. As you drift with these thoughts, as the mental image perhaps blurs into something more impressionistic than detailed, consider what else was hidden in those careful observations of 3I Atlas's coma structure. By late August, as the comet had moved significantly closer to the sun, and solar heating had intensified, the anti-tail structure began to fade. Not suddenly, not in a way that suggested something had broken or failed, but gradually, naturally, as the physics governing the coma shifted to accommodate the changing thermal environment. The explanation, pieced together from modelling and observation, revealed another layer of subtlety in how ice behaves under solar radiation. As the comet approached perihelion, as temperatures rose and sublimation rates increased, the survival time of ice grains decreased across the board, but it decreased most dramatically for grains travelling sunward, for those particles experiencing the strongest heating and the most asymmetric mass flux. Eventually, by early September, the thermal conditions had changed enough that even in the favourable geometry of sunward travel, ice grains could not survive long enough to create an extended structure. The antitail disappeared, replaced by a more conventional appearance, a dust tail stretching in the antisolar direction, as radiation pressure pushed the larger, longer-lived particles that could still survive the increasingly harsh environment. But this transition itself was informative. It was telling astronomers something about the size distribution of particles being released from the nucleus, because the timing of when the antitail faded depended critically on how large the ice grains were, how much thermal mass they possessed, and how quickly they could sublimate away under increasing solar flux. The observations suggested grains with effective radii around 1/10 of a millimetre, particles just large enough to see with a good microscope, but far too small to see individually from Earth. Even with our best telescopes, these grains, neither the microscopic dust that dominates some comets, nor the pebble-sized chunks that others produce, represented something in between, a size regime that might tell us something about how ice aggregates in the nucleus, or how fragmentation occurs during the violent sublimation processes that eject material into space. And here is something fascinating about those grain sizes, something that connects to deeper questions about how cometary nuclei are structured and how they evolve. Very small particles, the micron-sized dust grains that form the finest component of cometary tails, should be abundant if the nucleus is fragmenting randomly, if pieces of all sizes are being liberated as ice sublimates and mechanical stresses build. But 3I Atlas seemed relatively depleted in these smallest particles. The light scattering properties of its coma, the way brightness varied with wavelength and with scattering angle, suggested that larger grains dominated the cross-section, that most of the sunlight we saw reflecting from the coma was bouncing off particles 100 times larger than the finest dust. This depletion might reflect something about particle cohesion, about how ice grains stick together through weak intermolecular forces. Small particles have higher surface area relative to their mass, which makes these cohesive forces relatively more important. If ice grains tend to stick together, tend to aggregate rather than dispersing as individuals, then perhaps the smallest particles get bound into larger aggregates, creating the size distribution we observe. Alternatively, and this is where speculation becomes necessary, because we simply do not have enough data to distinguish between possibilities, perhaps the production mechanism itself favours larger particles. If ice is sublimating from beneath a surface crust, if pressure builds until that crust fractures and chunks break free, then the size of those chunks depends on the mechanical properties of the crust, on how thick it is and how brittle. A thicker crust might produce larger fragments. A more cohesive crust might resist fracturing until pressures are high enough to eject substantial pieces. We do not know, not with certainty. And perhaps by now, you're beginning to appreciate how much of this story consists not of firm answers, but of possibilities constrained by observations, of hypotheses that fit the data, but remain fundamentally uncertain, open to revision as new information arrives, or as theoretical models become more sophisticated. Let your consciousness rest with that uncertainty for a moment, with the idea that even something as seemingly simple as ice grains responding to sunlight contains layers of complexity that resist easy resolution, that invite continued study, careful thought, and the patient accumulation of observations across multiple apparitions of similar objects. As September progressed, and 3I Atlas continued its inexorable approach toward perihelion, the dust production rate, carefully measured by astronomers using photometric techniques that compare observed brightness to theoretical models, revealed another aspect of the comet's physics. At a distance of 2 astronomical units, roughly twice as far from the Sun as Earth orbits, 3I Atlas was producing approximately 180 kilograms of dust every second. Think about that for a moment. Every second, as you breathe in and out, as your heart beats once or twice, 180 kilograms of material that had been locked in that frozen nucleus since its formation billions of years ago, was being liberated into space, transformed from solid ice mixed with dust into a dispersing cloud of particles that would eventually be swept away by the solar wind or captured by the sun's gravity. That is roughly the mass of 2 adult humans every single second, continuously, as long as solar heating remains sufficient to drive sublimation. Multiply that by the minutes and hours and days of active outgassing, and the total mass loss becomes substantial, perhaps a significant fraction of the entire nucleus, certainly enough to expose fresh ice layers and potentially to alter the comet's structure, or even trigger fragmentation if internal stresses became too great. The comparison with 2I Borisov, the second interstellar visitor and the only other interstellar comet we have studied in detail, was instructive here, at the same solar distance. Borisov was producing roughly 70 kilograms per second, less than half the rate of 3I Atlas, despite being similar in many other respects. This difference might reflect different compositions, different volatile abundances, different nuclear structures, or it might simply be a consequence of timing, of where each object was in its activity cycle when we happen to observe it. Comets do not produce dust at constant rates. They flare and subside. They develop active regions and quiet regions. They respond in complex ways to the changing thermal environment as they approach and recede from the sun. But regardless of the explanation, the observations made clear that 3I Atlas was an energetic object, vigorous in its response to solar heating, transforming itself in real time as we watched, with our arrays of telescopes and spectrographs and photometers. Now, as the coma continued to expand and evolve, another process was operating, one that would eventually create the more conventional dust tail that replaced the early anti-tail structure. This process, called radiation pressure sorting, represents one of the most elegant examples of how simple physics can create complex outcomes. Sunlight carries momentum. When photons strike a surface and either reflect or are absorbed, they transfer that momentum to whatever they hit. For large objects, this radiation pressure is negligible. Completely overwhelmed by gravitational forces, Earth feels radiation pressure from the Sun, but that force is vanishingly small compared to the gravitational attraction that holds us in orbit. But for small particles, especially ones with a large surface area relative to their mass, radiation pressure becomes significant. A dust grain in the coma of 3I Atlas feels both the gravitational pull of the tiny nucleus, negligible at distances of more than a few kilometers, and the outward push of sunlight, gentle but persistent, and always acting in the anti-solar direction. The key insight is that this radiation pressure scales differently than gravity does with particle size. For smaller particles, with their higher surface-to-mass ratio, radiation pressure dominates. For larger particles, gravity matters more. The result is a natural sorting mechanism, a kind of spectroscope of dust, where different regions of the tail contain different size particles. Closest to the nucleus, a mix of all sizes, recently ejected, and not yet sorted by their different responses to radiation pressure. Farther out, the smallest grains, blown back most vigorously by sunlight, forming the finest streamers of the tail. Farther still, progressively larger particles, each size moving at its own characteristic velocity, creating layers and structure in the tail that careful observation can detect and analyze. By studying how light scatters from different regions of 3I Atlas's tail, by measuring subtle color differences that reflect the wavelength-dependent scattering properties of particles of different sizes, astronomers could infer the size distribution of dust being produced, could map out which sizes were abundant and which were rare. And this mapping, this careful analysis of light scattered by particles we can never see individually, revealed that 3I Atlas was producing primarily particles in that intermediate size range we discussed earlier, the 100-micron grains that dominated the coma's cross-section. The finest dust was present, but not abundant. The largest chunks were rare. Most of the mass being ejected existed in this middle ground, in grains large enough to survive for extended periods, but small enough to be lifted by gas drag, as volatiles sublimated beneath them. Perhaps you are wondering, as your thoughts drift and fragment in ways that signal sleep's approach, why all of this matters. why we should care about grain sizes and sublimation rates, and the subtle physics of how ice responds to sunlight. And the answer, both immediate and profound, is that these details tell us about processes we cannot directly observe, about the interior structure of an object we will never touch, about formation conditions that existed billions of years ago in a system we cannot visit. Every measurement constrains possibilities. Every observation eliminates some hypotheses while supporting others. The collective weight of these tiny details, none decisive alone, but together forming a coherent picture, gradually reveals the nature of this visitor in ways that transcend any single measurement. We have drifted now, through the physics of ice and light, through survival times and radiation pressure, through grain sizes and mass loss rates, through all the invisible processes that create the visible phenomenon we call a comet. The anti-tale that initially puzzled observers emerged from nothing more exotic than careful attention to geometry and sublimation asymmetry. The dust tail that replaced it formed through the patient operation of radiation pressure, sorting particles by size. The evolution from one state to another reflected changing thermal conditions as 3I Atlas moved through its perihelion passage. All of it, every observation, every structure, every change in appearance, emerges from basic physics operating on a collection of ice and dust that happens to be passing through our solar system on a trajectory that will carry it back to the galactic depths from which it came. There is no mystery in the mechanisms, no unknown forces at work, just ice responding to heat, dust responding to light pressure, matter obeying the laws that govern all matter everywhere. And yet, somehow, in the details of how these simple processes create complex outcomes, in the way geometry and timing and composition combine to produce unique appearances, there exists something worthy of wonder, something that repays careful attention and patient study, with insights into not just this particular object, but the broader processes that operate throughout our galaxy. The night is deep now. The physics have been laid bare, the mechanisms explained as well as current knowledge allows, and somewhere in the solar system, 3I Atlas continues its journey, continues sublimating and producing dust and evolving in appearance as conditions change, indifferent to our attempts to understand it, simply being what it is, ice and rock following the dictates of physics, responding to forces according to rules that transcend all questions of origin or destination. Rest now, knowing that what seems complex often emerges from simple rules, operating in intricate combination. That understanding requires patience and careful observation, and a willingness to sit with uncertainty, while accumulating the small pieces of evidence that eventually coalesce into knowledge. Incomplete knowledge, perhaps, but knowledge nonetheless, hard-won, from the careful study of light and motion, and the way ice behaves when warmed by a sun that is not its own. We have traced the chemistry, explored the physics, watched as 3I Atlas transformed from dormant wanderer to active comet under our sun's patient warming. Now, as October approached, and the comet continued its inexorable journey toward perihelion, another dimension of this story began to unfold, one involving not just passive observation from Earth, but potential encounters with the machinery humanity has scattered throughout the inner solar system. Let your mind settle deeper now as we explore what happened when this visitor from beyond crossed paths with worlds both natural and artificial, when the geometry of orbital mechanics created opportunities for observation that occur perhaps once in a lifetime, perhaps once in the entire history of a civilization's spacefaring capabilities. The calendar, indifferent to human hopes and astronomical significance, simply marked the passing days, September fading into October, autumn arriving in the northern hemisphere, while spring awakened in the south, seasons cycling as they always do, while something genuinely unprecedented unfolded in the space between planets. On October 3rd, 2025, 3I Atlas passed within 30 million kilometers of Mars. 30 million kilometers. It sounds vast, and by earthly standards it is vast. a distance that light requires nearly 2 minutes to cross, a gap that would take our fastest spacecraft months to traverse. But in astronomical terms, in the context of solar system distances, and the scales across which gravitational influence operates, this was remarkably close. Close enough that every instrument humanity had placed in Mars' orbit, or landed on its rusty surface, could potentially observe this visitor, could turn their sensors towards something that had never been part of Mars's cosmic neighbourhood, picture, if you will, the perspective from Mars itself. The sky there, that butterscotch dome tinged with perpetual dust, would have shown 3i Atlas as a faint smudge, perhaps visible to a patient observer with good instruments, but nothing like the spectacular cometary displays that occasionally grace Earth's skies. The comet was not putting on a show for Mars, was not approaching close enough for dramatic effect, but it was there, present in Mars's sky, moving against the background stars in ways that marked it as something different, something near rather than distant, and watching from orbit, an array of spacecraft, representing decades of international effort and billions in investment, turned their attention from their primary missions to spend precious observation time studying this cosmic visitor. The European Space Agency's Mars Express, orbiting the red planet since 2003, adjusted its instruments. The ExoMars Trace Gas Orbiter, designed to study the Martian atmosphere's subtle chemistry, pointed its spectrographs toward the comet instead. Even the rovers on the surface, patient robots that had spent years analysing rocks and soil, looked up, capturing what images they could of this visitor passing through their alien sky. What made this encounter particularly valuable from a scientific perspective was not just the proximity, though that certainly mattered. Rather, it was the geometry, the fact that spacecraft at Mars could observe 3i Atlas from angles impossible to achieve from Earth, creating a stereoscopic perspective that revealed three-dimensional structure in the coma and tail. When you observe an object from a single point, you see a two-dimensional projection of its three-dimensional structure. You can infer depth through various techniques, through how light scatters or how brightness changes, but there is always ambiguity, always multiple possible configurations that could produce the same observed appearance. But with observations from two widely separated locations, Earth and Mars in this case, that ambiguity largely disappears. The different viewing angles reveal structure directly, show which features are truly extended in space, and which are merely projections or perspective effects. For 3i Atlas, this multiple viewpoint observation potentially revealed details about the true shape of the anti-tail structure we discussed earlier, about whether the coma was truly asymmetric, or whether some of that apparent asymmetry was an artifact of viewing geometry. It might have shown rotation of the nucleus through slightly different phase angles, allowing better constraints on the spin axis orientation and rotation period. But here is where the story takes an even more intriguing turn, where the careful planning of mission trajectories and the fortunate timing of 3i Atlas's arrival created an opportunity that no one had anticipated when these spacecraft were launched years earlier. Europa Clipper, the National Aeronautics and Space Administration's ambitious mission to study Jupiter's ice-covered moon Europa, launched in 2024, and was at this time making its way through the inner solar system, on a trajectory that would eventually carry it to the Jovian system, on its journey outward, following a path calculated years in advance to take advantage of gravitational assists and minimise fuel requirements. Europa Clipper happened to be positioned in a region of space where something remarkable might occur. The comet's ion tail, that stream of charged particles stripped from the coma by the solar wind and accelerated to velocities far higher than the neutral dust we have discussed, extended millions of kilometres behind 3i Atlas along its orbital path. Unlike the dust tail, which curves gently under the influence of radiation pressure, the ion tail stretches nearly straight back from the Sun, aligned with the magnetic field lines embedded in the solar wind, creating an invisible highway of charged plasma. And Europa Clipper's trajectory, through a coincidence of orbital mechanics that seems almost too perfect to be mere chance, carried it through a region where models predicted this ion tail might extend. Think about what that means for a moment, as your breathing perhaps slows further, as the narrative becomes less a sequence of facts and more a contemplation of cosmic serendipity. A spacecraft built to study one of Jupiter's moons, launched before we even knew 3I Atlas existed, following a trajectory calculated to optimize fuel use and arrival timing, happened to pass through space at precisely the right time and place, to potentially fly through the ion tail of an interstellar comet. The encounter, if it occurred as predicted, would have lasted perhaps a week in late October, from roughly October 30th through November 6th. During that time, Europa Clipper's instruments, designed to measure magnetic fields and charged particles in Jupiter's complex magnetosphere, would have recorded any changes in the local plasma environment caused by material from 3I Atlas. Would they have detected anything? The predictions were uncertain, the models tentative. Ion tails are diffuse, their particle densities low even at their densest. The chance of Europa Clipper passing through a region with detectable ion concentrations depended on factors we could not perfectly predict: the exact production rate of ionized molecules from the comet, the precise configuration of the interplanetary magnetic field at that time, the detailed dynamics of how those ions were accelerated and dispersed by the solar wind. But the possibility existed, and that possibility alone represented something profound. If Europa Clipper's magnetometer detected anomalous magnetic field signatures, if its plasma instruments recorded unusual particle fluxes during that predicted window, it would mark the first time a spacecraft had directly sampled material from an interstellar object, had flown through and measured the composition and properties of matter from another stellar system. Not through remote observation, not through spectroscopy or photometry, but through direct measurement, through instruments designed to count particles and measure their properties one by one. The data, if it existed, would be different in kind from everything else we had gathered about 3I Atlas, complementary to the remote observations, but operating at a different level of directness, of immediacy. And Europa Clipper was not alone in this potential encounter. Another spacecraft, the European Space Agency's Hera mission, launched to study the asteroid Didymos and the results of the Amerika Birleşik Devletleri Ulusal Havacılık ve Uzay Dairesi'nin DART impact test, was also traversing the inner solar system during October 2025. Hera's trajectory, like Europa Clipper's, carried it through regions where models suggested the ion tail might extend, creating a second opportunity for in situ sampling of interstellar material. The timing for Hera was slightly earlier, from approximately October 25th through November 1st, a window that overlapped with, but was not identical to, Europa Clipper's potential encounter. Two spacecraft, launched for different purposes, following different paths, both potentially passing through the same structure extending behind this visitor from beyond. Perhaps, as you drift now between waking and sleeping, between conscious thought and dream, you can appreciate the extraordinary coincidence of it all. The way the universe occasionally arranges circumstances that seem designed to facilitate discovery, that create opportunities no amount of planning could have anticipated. These spacecraft were not built to study comets, were not launched with 3I Atlas in mind, yet here they were, positioned to potentially make measurements that dedicated comet missions might envy. But while these potential encounters represented opportunities for direct sampling, the main event, the climax toward which all of 3I Atlas's inward journey had been building, was still approaching. Perihelion. That point of closest solar approach loomed at the end of October like a destination marked on a cosmic calendar since the moment we first calculated the comet's trajectory. October 31st. Halloween, as it happens. Though the universe cares nothing for human holidays, and the timing was pure coincidence. On this date, 3I Atlas would reach its closest approach to the Sun, approximately 1.4 astronomical units, placing it inside the orbit of a Mars, but well outside Earth's path, at a distance where solar heating would reach maximum intensity. This was the moment astronomers had been anticipating since July, the point where all their models suggested activity would peak, where sublimation rates would maximize, where the most volatile ices would finally begin to contribute to the outgassing that drove the visible coma. This was when 3I Atlas would reveal whatever secrets remained hidden beneath its surface layers, when thermal waves penetrating the nucleus would reach depths that had stayed frozen throughout the comet's journey inward. But here is the cruel irony. The cosmic joke that nature played on the astronomers who had spent months planning their observing campaigns, writing proposals for a telescope time, and coordinating international efforts to maximise coverage of this unprecedented event. Just as 3i Atlas reached perihelion, just as it achieved maximum activity and maximum interest, it passed behind the Sun from Earth's perspective. Superior conjunction, the astronomers called it. That configuration where an object lies on the far side of the Sun as seen from Earth. During this period, roughly from mid-October through early November, the comet was essentially unobservable from our planet, too close to the Sun's glare in the sky, too aligned with our star to separate its faint light from the overwhelming brightness that drowns out everything else. The timing could not have been worse, or more perfect, depending on your perspective. If you believe the universe has a sense of humour, this would be prime evidence. If you understand that orbital mechanics operates without regard for human convenience, this was simply an inevitable consequence of geometry and timing. Disappointing, perhaps, but not surprising. The spacecraft at Mars had their window of opportunity in early October, before superior conjunction made Earth-based observation impossible. Europa Clipper and Hera might sample the ion tail in late October, during the period when Earth's view was blocked, but the peak activity, the moment of maximum sublimation and potential outburst or fragmentation, would occur while humanity's most powerful telescopes could not see the comet at all. It was like attending a concert where the lights go out during the featured solo, like reading a mystery novel with pages missing at the moment of revelation. Frustrating, certainly, but also somehow fitting. A reminder that the universe does not arrange itself for our convenience, that cosmic events proceed according to their own schedules, regardless of whether we are positioned to observe them. What we could predict, what the model suggested with varying degrees of confidence, painted a picture of what might be happening during those unobservable weeks. The thermal models, refined through months of observations as 3i Atlas approached, predicted that perihelion would trigger a significant increase in water ice sublimation. Through most of the inbound journey, activity had been driven primarily by more volatile substances, carbon monoxide and carbon dioxide, whose sublimation temperatures are much lower than water's, but at perihelion, surface temperatures would finally rise enough that water ice could contribute meaningfully to the outgassing. This shift, from carbon monoxide-dominated to water-dominated activity, represents a fundamental change in cometary behaviour, one that affects everything, from dust production rates to coma chemistry to the appearance and evolution of the tail. Water molecules, once liberated from the nucleus, interact differently with solar radiation than carbon monoxide does. They create different spectral signatures, participate in different chemical reactions, produce different ionic species when ionized by ultraviolet light, and if water was finally beginning to dominate the sublimation budget, if thermal waves had penetrated deep enough to reach pristine ice deposits that had never been warmed before, there was potential for outbursts, for sudden increases in activity, as pressurized volatiles found escape routes through the overlying crust, or as weakened crust collapsed inward and exposed fresh material. Comets often behave unpredictably near perihelion. The combination of maximum heating, maximum thermal stress, and potential structural weaknesses can trigger fragmentation events, sudden brightenings, or changes in rotation rate as mass is ejected asymmetrically. We could not know whether 3i Atlas would remain stable through its perihelion passage, or whether it might break apart, revealing its internal structure in the most dramatic way possible. The observations we did have, taken in late September and early October, before the sun's glare made further observation impossible, suggested the comet was holding together, that its structure was stable enough to survive the increasing stress. But predictions of cometry, behaviour are notoriously uncertain, complicated by factors we cannot measure remotely, by internal structures we cannot see, by mechanical properties we can only infer. Perhaps, as your consciousness drifts further towards sleep, as these details begin to blur into impressions and possibilities rather than concrete facts, you can hold the image of 3i Atlas, passing through its perihelion behind the sun's glare, invisible to human observation, but nonetheless real, nonetheless transforming under maximum solar heating, nonetheless continuing its journey according to physics that operates, whether we are watching or not. The encounters, these moments when worlds and spacecraft and cometary tails aligned in ways that created opportunities for unique observations, represented humanity's attempts to study this visitor as completely as our current capabilities allowed. Not all opportunities could be seized. The timing of perihelion relative to Earth's position meant the most dramatic moment would go unobserved from our planet. But the Mars flyby provided multiple viewing angles. The potential ion-tail encounters offered chances for direct sampling. The observations we could make, taken together, would still represent the most comprehensive study of an interstellar comet ever attempted. And when 3i Atlas emerged from behind the Sun in mid-November, when Earth-based telescopes could finally observe it again, they would be looking at an object that had been fundamentally transformed by its perihelion passage. The pristine material that had dominated its early activity would be depleted. The most volatile ices would be exhausted, or buried beneath layers of refractory material. The structure itself might be changed, weakened by thermal stress, or even fragmented into multiple pieces, if internal pressures had exceeded the strength of the weakest materials holding the nucleus together. But that is a story for another telling, for observations yet to be made and analysed, for papers yet to be written about what emerged from the solar glare, and how it differed from what went in. For now, for this moment as you rest in darkness, and the narrative of 3i Atlas continues its gentle unfolding, the important thing is the encounters themselves, these moments when our instruments and spacecraft and orbiting machinery were positioned to observe or sample this visitor in ways unique to each configuration. The universe arranged the geometry. We built the instruments and placed them where they needed to be, sometimes deliberately, sometimes through fortunate coincidence, and together, these human capabilities and cosmic arrangements created opportunities to learn things about this visitor that would have been impossible from Earth alone, to gather data from multiple perspectives, and potentially from direct sampling, that would enrich our understanding in ways remote observation could never achieve. Rest now, knowing that worlds turn, and spacecraft travel their calculated paths, and comets follow trajectories determined billions of years ago, by whatever event ejected them from their home systems, and sometimes, just sometimes, these independent motions align in ways that allow brief moments of encounter, fleeting opportunities to observe and measure and wonder at what passes through the darkness between stars and occasionally crosses our cosmic neighbourhood on journeys that dwarf all human timescales. We have followed 3i Atlas through its discovery, analysed its chemistry and physics, watched as it passed near worlds both natural and artificial. Now, as you rest deeper still, as consciousness perhaps hovers at the very edge of sleep's embrace, we turn to a question that might seem impossible to answer. Where did this visitor come from? Not in the immediate sense, not which direction it arrived from. That is simply a matter of calculating trajectories and tracing orbits backward through space. Rather, the deeper question, which star did it orbit? Which planetary system gave it birth? What sun warmed the materials that eventually coalesced into this frozen wanderer, now passing through our cosmic neighbourhood? The mathematics of orbital mechanics are precise, elegant in their determinism, given an object's position and velocity at any moment. Given knowledge of the gravitational fields it moves through, you can calculate where it was in the past or where it will be in the future with arbitrary precision, limited only by measurement uncertainties and computational resources. For 3i Atlas, we knew its position and velocity with remarkable accuracy by late 2025. Months of careful observations from telescopes around the world had refined the orbital parameters to high precision. We could predict where it would be years in the future, could calculate where it had been years in the past, could trace its path through the solar system with confidence. But to trace it farther back, to follow its trajectory through interstellar space toward whatever stellar system might have been its home, required something more ambitious, something that pushes against the boundaries of what computational astronomy can achieve. Because once you leave the region dominated by a single star's gravity, once you enter the realm where multiple stars' influences compete and overlap, the calculations become vastly more complex. The galaxy is not empty space with occasional stars scattered through it, like islands in an ocean. Rather, it is a dynamic system, where hundreds of billions of stars orbit the galactic centre in complex patterns, where stellar motions are influenced not just by nearby neighbours, but by the collective gravitational field of the entire galactic disk, where dark matter halos add invisible but very real gravitational effects. To trace 3i Atlas backward through this environment required integrating its orbit not just through empty space, but through a time-varying gravitational field, produced by stars whose positions and velocities themselves had to be tracked, as they too orbited through the galaxy. It required accounting for how the galaxy's structure changes over millions of years, how the spiral arms drift, and how stars migrate inward or outward through galactic radius. And critically, it required knowing which stars existed where, what their masses were, what their velocities were, so that close encounters could be identified and their gravitational effects properly calculated. Enter the European Space Agency's Gaia mission, that remarkable spacecraft orbiting at the second Lagrange point, patiently measuring the positions, proper motions and distances of more than 1 billion stars with unprecedented precision. Gaia's third data release, published in the years before 3i Atlas's discovery, provided exactly the information needed: positions, velocities, and distances for hundreds of millions of stars, enough to populate the local galactic neighbourhood with real data rather than statistical models. A team of astronomers, motivated by the profound question of where this visitor originated, undertook what amounts to one of the most ambitious computational astronomy projects ever attempted for a single object. They took 3i Atlas's precisely measured orbit and integrated it backward through time, simultaneously integrating the orbits of every Gaia star within 500 parsecs, approximately 1600 light-years, watching as both the comet and the stars traced their paths through the galaxy's gravitational landscape. 10 million years. That is how far back they calculated, a span of time that encompasses the entire history of recognizable human ancestors. A span that reaches back before the genus Homo existed, before the great ice ages of the Pleistocene, before any creature on Earth could look up at the night sky and wonder what moved among the fixed stars. Let your mind rest with that timescale for a moment, as your breathing perhaps slows even further, as the boundary between thought and dream becomes increasingly uncertain. 10 million years ago, whatever star system gave birth to 3i Atlas might have looked very different than it does now. Planets were in different configurations, if they still existed at all. The star itself was younger, perhaps more active, perhaps still hosting a disk of debris and planetesimals, from which new worlds might form. And 3i Atlas, freshly ejected from that system, by some gravitational perturbation, or stellar encounter, or migration of a giant planet, began its journey through the galaxy. Moving at tens of kilometers per second relative to the local standard of rest, that frame of reference representing the average motion of stars in the solar neighbourhood, it drifted through the galactic disk like a mote of dust suspended in air, too small to affect anything, but affected by everything massive enough to generate significant gravity. Through the spiral arms where stellar density increases and gravitational perturbations become more frequent. Through quieter regions between the arms, where stars are sparse and space approaches something resembling true emptiness, past molecular clouds, those dark nebulae where new stars are born and where gas densities might be high enough to create faint but measurable drag. Through regions where supernovae exploded and sent shockwaves rippling through the interstellar medium, all of this motion, all these potential influences, captured in the computational integration that traced 3i Atlas's probable path backward through 10 million years of galactic time. And what did they find? These astronomers who dedicated months of computer time and careful analysis to this question. What answers emerged from this computational archaeology, this attempt to trace a single frozen object back through millions of years to whatever birthplace might have launched it into the dark? 93 nominal encounters with stars from the Gaia catalogue, 93 moments in the past 10 million years. when 3I Atlas passed within 2 parsecs, roughly 6.5 light-years, of a catalogued star. Close enough that gravitational perturbations might have been significant. Close enough that one might suspect a connection, a shared history, perhaps even a common origin. Each encounter was analysed carefully, the relative velocity calculated, the closest approach distance determined, the gravitational perturbation that the encounter would have produced, computed from basic physics. And each encounter, when examined in detail, when subjected to statistical analysis that accounted for uncertainties in both 3I Atlas's trajectory and the star's positions and velocities, revealed the same disappointing conclusion. No significant perturbation, no encounter close enough or slow enough to have meaningfully altered 3I Atlas's trajectory. No obvious candidate for a parent star system. The strongest perturber, a star designated in the Gaia catalogue by a long string of numbers that means something to astronomers, but nothing to anyone else, passed within 0.3 parsecs, roughly 1 light-year, of 3I Atlas's calculated position, approximately 3 million years ago. The relative velocity at that encounter was 35 kilometers per second, not dramatically fast by galactic standards, but fast enough that the interaction time was brief, the gravitational influence minimal. The change in 3I Atlas's velocity from that encounter amounted to less than a millimeter per second. 1 millimeter per second, about the speed at which a falling snowflake might drift in still air. Utterly negligible compared to the comet's overall velocity through the galaxy, completely insufficient to explain how it arrived at our solar system on the trajectory we observed. Perhaps you're feeling, as you drift closer to sleep's embrace, a sense of anticlimax, of disappointment that this computational detective work did not point clearly to a stellar home, did not solve the mystery of origin with satisfying finality. And certainly, the astronomers who conducted this analysis felt that disappointment, wrote in their papers about the negative result, about the absence of any clear connection to any known star. But here is what makes this negative result actually profound, actually revealing, in ways that a simple answer would not have been. It tells us something about the nature of galactic space, about the vast distances between stars, about how isolated stellar systems truly are, despite residing in a galaxy with hundreds of billions of neighbours, even over 10 million years, even tracing backward through that immense span of time, even checking 93 different stellar encounters. None of them proved significant. None of them dominated 3I Atlas's trajectory. None of them imparted the energy or direction that would explain the comet's current path through space. This means 3I Atlas's ejection from its parent system likely occurred more than 10 million years ago, perhaps much more. It means this object has been wandering through interstellar space for a duration that exceeds the computational reach of even Gaia's comprehensive stellar catalogue. That predates our ability to accurately reconstruct stellar positions, because proper motions compound uncertainties over such timescales. Or perhaps, and this is equally humbling, it means the parent star is not in Gaia's catalogue at all. Perhaps it is fainter than Gaia can detect at relevant distances. Or perhaps it lies outside the 500 parsec radius that the study examined. Perhaps 3I Atlas was ejected from a stellar system that is now hundreds or thousands of light years away, so distant that even 10 million years is not enough time to erase the effects of that ancient ejection, to randomize the comet's trajectory through galactic gravitational interactions. The kinematic analysis revealed one more interesting detail, one more piece of the puzzle that constrains possibilities without fully solving the mystery. 3I Atlas's velocity and trajectory are consistent with what astronomers call the thin disk population, that component of the galaxy where younger stars orbit in relatively circular paths, close to the galactic plane. This is the population that includes our own Sun, that contains most of the stars visible to the naked eye, that represents the galactic region where ongoing star formation produces new stellar systems and planetary families. Being kinematically consistent with the thin disk suggests 3I Atlas likely formed from materials enriched by multiple generations of stellar evolution, that it contains heavy elements produced in supernovae and dispersed through the galactic disk over billions of years. But here is what makes this finding puzzling. 3I Atlas's peculiar velocity, its motion relative to the local standard of rest, is large by thin disk standards. Most thin disk objects, including the Sun, move at velocities within a few tens of kilometers per second of the local average. 3I Atlas moves considerably faster, suggesting something energetic happened in its past, some event that accelerated it significantly above the typical velocities for its galactic population. That event was almost certainly its ejection from whatever planetary system originally hosted it. Gravitational interactions with giant planets can impart substantial velocity changes to smaller objects, can eject comets from planetary systems at speeds high enough to become unbound, not just from the star, but from the typical velocity distribution of the stellar population. So we have, in the end, not answers, but refined questions. Not a clear identification of 3I Atlas's origin, but rather constraints on possibilities, boundaries that tell us what it is not, even if they cannot tell us definitively what it is. It is not from any star system whose encounter with the comet in the last 10 million years left a detectable signature. It is not from the thick disk or halo populations that contain the galaxy's oldest stars. It likely formed within the last few billion years, in a stellar system similar in some ways to our own, in a region of the galactic disk where star formation has been active, and where chemical enrichment from dying stars has produced metals and organic molecules in abundances comparable to what we see locally. Beyond that, the trail goes cold, lost in the vastness of galactic space and the deep time of the comet's wandering journey. Perhaps there is something appropriate about this uncertainty, something that fits the larger theme of 3I Atlas as a visitor about whom much remains mysterious. We can analyse its chemistry and puzzle over unusual abundances. We can study its physics and model how ice responds to solar heating. We can watch as it passes our planets and perhaps flies through the instruments of our spacecraft. But we cannot, despite our best computational tool and comprehensive stellar catalogues, definitively identify where it came from. We cannot point to a star and say with certainty that this is its home. As your thoughts drift now, as the details perhaps blur into impressions, and the narrative becomes more feeling than fact, consider what this means for our understanding of the galaxy we inhabit. We live in a system where stars are separated by distances so vast that even objects moving at tens of kilometers per second require millions of years to traverse interstellar space, where ejection from a planetary system sends objects on trajectories that carry them through multiple spiral arm passages, through encounters with dozens of stars, none close enough to significantly alter their paths. This is a galaxy where isolation is the norm, where stellar systems are islands, separated by gulfs of space that render them essentially independent, despite sharing the same galactic disk. The exchange of materials between systems occurs not through frequent interactions, but through rare events, through the occasional comet that wanders long enough and far enough to eventually encounter another star's gravity well, and perhaps become captured, becoming part of a new system, light years from its origin. 3I Atlas is one such wanderer, though in this case not captured, merely passing through, on a trajectory that will carry it back out into the galactic disk, back into the vast spaces between stars, where it will continue its journey for epochs we cannot calculate, toward destinations we cannot predict, carrying within its frozen nucleus the chemical signatures of a birthplace we cannot identify. The search for its home, ambitious as it was, revealed primarily the limitations of our ability to trace objects through galactic time. 10 million years sounds vast, and by human standards it is vast. But by galactic standards it is merely a moment, a blink, in the 4 billion year lifetime of stars like our Sun. The galaxy remembers very little about motions from 10 million years ago, and beyond that boundary, our ability to reconstruct the past dims rapidly, becomes increasingly uncertain, eventually becomes pure speculation, constrained only by statistical arguments about what is probable, rather than concrete data about what actually occurred. And so we are left with mystery, with questions that remain open despite months of observation and years of analysis that might follow. We know what 3I Atlas is, an interstellar comet, a frozen remnant of planetary formation around some distant star. We know what it contains: water and carbon dioxide, organic molecules, metals in unusual ratios, chemistry that reflects conditions different from our solar system's formation environment. But we do not know where it came from. Not specifically, not in a way that allows us to point at a star and feel confident in the identification, and perhaps we never will. Perhaps this particular mystery will remain unsolved, one of those questions that astronomers will continue to work on, but might never fully answer, might pass on to future generations, with better instruments and more comprehensive catalogues to continue the search. The night is deep now, deeper than it has been through this entire journey with 3I Atlas. The search for origins has led not to answers, but to a confrontation with the vastness of space and time, with the limitations of our knowledge and capabilities, with the humbling reality that some questions might exceed our ability to answer them, at least for now, at least with the tools and data currently available. Rest now, knowing that mystery is not failure, that unanswered questions are not defeats, but rather invitations for continued exploration, continued refinement of techniques, continued patience as new capabilities emerge and new data becomes available. 3I Atlas came from somewhere, that much is certain. From a star we have not identified, from a planetary system whose architecture we can only imagine, from conditions that produced chemistry just different enough from our own to mark it as foreign. Somewhere in the galaxy, perhaps a few hundred light years away, perhaps thousands, a star continues shining, unaware that one of its ancient children has travelled to our solar system and briefly graced our instruments with its presence, before continuing its eternal wandering through the galactic dark. We may never know which star, may never identify the specific system. But we know it exists, know it must exist, because 3I Atlas had to come from somewhere, had to originate in some stellar environment that gave it the chemistry and composition we observe. That knowledge, incomplete as it is, uncertain as it remains, is itself a form of connection across the light years, a recognition that we share this galaxy with countless other stellar systems, some of which occasionally send us the visitors that carry within their frozen structures evidence of distant processes and ancient histories that enrich our understanding, even when they resist complete explanation. Sleep now, cosmic traveller, and let the mystery of origins rest alongside you, unresolved perhaps, but not troubling. Simply there, simply part of the larger tapestry of questions that make astronomy not just a science, but a practice of sophisticated humility, where the more we learn, the more we recognise how much remains unknown. We have wandered through discovery and chemistry, through physics and encounters, through the search for origins that led not to answers, but to deeper questions about the galaxy we inhabit. Now, as this journey draws toward its gentle close, as you rest in whatever darkness surrounds you, with consciousness perhaps hovering at sleep's very threshold, we turn to something both simpler and more profound. What did this visitor teach us? What can we take away from months of observation and years of analysis that might follow? What meaning emerges from the accumulated details of this cosmic encounter? Let your breathing find its slowest rhythm now, natural and unhurried, as we step back from specifics and consider the broader picture, the ways in which 3I Atlas fits into humanity's expanding understanding of what exists beyond our solar system's comfortable boundaries. Before 3I Atlas, we had encountered 2 confirmed interstellar visitors, each one different, each one revealing something unexpected about the diversity of objects that wander between the stars. First came Oumuamua in 2017, that peculiar elongated object that tumbled through our inner solar system, moving far too fast to be captured, displaying no obvious cometary activity, despite passing close enough to the Sun that any significant volatile content should have sublimated. Its shape, inferred from brightness variations, suggested something long and thin, perhaps cylindrical or cigar-shaped, unlike any asteroid or comet we had seen before. Its trajectory showed slight deviations from a purely gravitational path, accelerations that might have been outgassing too faint to detect, or might have been something else entirely. Oumuamua sparked speculation precisely because it was so unusual, so unlike the mental category we label comet or asteroid. It forced astronomers to confront the possibility that objects from other stellar systems might not fit neatly into the classifications we have developed from studying our own solar system's population. It left more questions than answers. Departed before we could study it properly, became a Rorschach test onto which observers projected their expectations and concerns. Then, in 2019, came 2I Borisov, discovered by an amateur astronomer and immediately recognizable as a comet. Active coma, visible tail, spectroscopic signatures that match solar system comets in most respects. Borisov felt familiar, comfortable, like meeting a foreigner who speaks your language and shares your cultural references. Its composition showed some differences from solar system comets, subtle variations in the ratios of different carbon compounds, but overall it behaved exactly as a comet should behave, following the patterns we expect from icy planetesimals formed in the outer regions of a planetary system. Borisov reassured us, in a sense, that the basic physics of planetary formation operates similarly around other stars, that comets from other systems are not necessarily exotic or strange, that at least some interstellar visitors will be comprehensible within our existing frameworks of understanding. And now, 3I Atlas, arriving with its own unique combination of familiar and strange, challenging some expectations while confirming others, adding another data point to the emerging picture of what interstellar objects can be. Like Borisov, 3I Atlas showed clear cometary activity, developing a coma and tail, displaying spectroscopic signatures of sublimating volatiles. But unlike Borisov, its chemistry revealed unusual abundances, that extreme nickel-to-iron ratio we explored in earlier sections, the carbon dioxide production rates that exceeded models by factors of 100, the signs of exotic metal carbonyl compounds that might exist in cold, outer planetary regions, but do not appear in our solar system's comets. Its physics, too, revealed something unique, that anti-tail structure pointing sunward, created by the anisotropic survival of ice grains under asymmetric illumination. While the underlying mechanism involved nothing more than basic sublimation physics, the particular geometry and timing created a structure that initially puzzled observers, that required careful modelling to understand. Perhaps most intriguingly, 3I Atlas showed us that interstellar comets can become active remarkably far from the Sun, that the turn-on distance for cometary activity depends critically on composition, on which volatiles dominate the ice matrix. Its activity at 6 astronomical units, driven by carbon monoxide, carbon dioxide, or some combination of both, demonstrated that not all comets wait until solar heating intensifies before responding. The comparison of these 3 visitors, our entire sample of confirmed interstellar objects, reveals a pattern of diversity, a range of properties that suggest the universe produces many different kinds of small bodies through many different pathways. Some, like Oumuamua, might be fragments of disrupted planets, or the cause of comets that have lost all their volatile content through billions of years of processing. Some, like Borisov, might be relatively pristine comets, ejected from their formation zones before significant evolution could occur. Some, like 3I Atlas, might represent intermediate cases, or objects formed under specific conditions that leave characteristic chemical signatures. Each one teaches us something about what is possible, about the range of outcomes that planetary formation and evolution can produce. Each one constrains our models and refines our understanding, and each one, by existing at all, reminds us that our solar system is not isolated, that we participate in a galactic ecosystem, where materials move between stellar systems over timescales that dwarf human comprehension. Think about what that means for a moment, as your thoughts perhaps drift and fragment in ways that signal sleep's imminent arrival. the galaxy you inhabit is not a collection of isolated star systems, each developing independently without influence from neighbours. Rather, it is a connected network, where exchange occurs constantly, where supernovae distribute heavy elements across light years, where molecular clouds mix materials from multiple stellar generations, where objects like 3I Atlas carry samples from one system to another. Our solar system has almost certainly received visitors like this throughout its 4.5 billion year history. Most went undetected because they arrived before humans existed, or because they passed through the outer solar system without coming close enough to Earth to be easily observed. Some might have impacted planets or moons, delivering their exotic chemistry to surfaces, where it mixed with native materials and became indistinguishable from local composition. Earth itself might contain atoms that arrived aboard ancient interstellar visitors, might have incorporated materials from other stellar systems into its crust, its atmosphere, and its oceans. The distinction between our materials and their materials blurs over billions of years of exchange. As the galaxy's contents mix and homogenize, while still retaining pockets of distinctiveness, where local conditions produced unusual outcomes, this realization that we are part of something larger, that our solar system exchanges materials with the broader galaxy, changes the context in which we think about planetary formation and chemical evolution. We are not studying isolated systems that developed in complete independence. We are studying nodes in a network, participants in processes that operate across galactic scales, connected through the slow but steady exchange of materials that wander between stars. Perhaps there is something comforting about this interconnection, this recognition that isolation is never complete, that even across the vast gulfs between stellar systems, exchange occurs, materials move, information gets transferred through the compositions and structures of wandering objects. We live in a universe where nothing is truly alone, where everything participates in larger cycles and systems that create connections spanning unimaginable distances. The lessons 3I Atlas teaches extend beyond the specific details of its composition or behaviour. They touch on something fundamental about how science works, about the relationship between observation and understanding, about the value of questions that resist easy answers. We learned that detailed observations of even brief encounters can reveal extraordinary amounts of information. Months of spectroscopy and photometry, careful measurements of brightness variations and molecular emission lines, patient analysis of coma structure and tail morphology. All of this accumulated into a comprehensive picture of an object we will never touch, never sample directly, that spent only a few months close enough for detailed study before receding back into the darkness from which it came. We learned that negative results carry information, that the failure to identify 3I Atlas's parent star tells us something important about galactic dynamics and timescales, about how long objects wander and how isolated stellar systems truly are. The absence of clear stellar encounters in the past 10 million years constrains possibilities, eliminates hypotheses, refines our understanding, even though it does not provide the satisfying closure of a definitive answer. We learned humility, perhaps, or were reminded of it. The universe is vast beyond our ability to fully comprehend, operates on timescales that make human lifetime seem like eye blinks, contains complexities that resist simple explanation, even when the underlying physics is well understood. Every answer generates new questions. Every observation reveals new puzzles. The boundary of knowledge expands, but never disappears, always recedes before us, like a horizon that can be approached, but never quite reached. And we learned about ourselves, about what drives human curiosity, about why we devote resources and careers and years of patient effort to studying something as seemingly insignificant as a small chunk of ice passing through our cosmic neighbourhood. Because it is not really about the ice, not fundamentally. It is about understanding, about connection, about the deep satisfaction that comes from reading the universe's messages, written in chemistry and orbital mechanics, and the subtle physics of how matter responds to energy. 3I Atlas carried information, not intentionally, not as a message deliberately sent, but simply by being what it is, by preserving in its composition and structure, evidence of processes and conditions that exist elsewhere, that operate around other stars, that create outcomes different from, but related to, what we see in our own familiar surroundings. Reading that information, extracting meaning from spectral lines and photometric curves, translating observations into understanding. This is what astronomers do, what drives the field forward, despite the challenges and uncertainties, and the frequent frustrations when nature refuses to cooperate with human schedules and preferences. As you drift now, perhaps barely conscious of these words, perhaps already slipping into dream, while some part of your mind still follows this gentle narrative, consider one final aspect of what 3i Atlas represents. It is a glimpse of a future that is already beginning to unfold. For most of human history, for all of human history until very recently, interstellar objects were purely theoretical. We knew they should exist, knew that planetary systems must eject objects into interstellar space, knew that the galaxy should be filled with wanderers making their slow journeys between stellar systems, but we had never seen one, never confirmed that these theoretical objects actually existed in observable reality. Now, in less than a decade, we have found 3. Not because the rate of interstellar visitors has suddenly increased, but because our survey capabilities have finally reached the threshold where detecting these objects becomes possible. Better telescopes, better cameras, better software for identifying moving objects against the background stars. All of this has opened a window onto a population that was always there, but remained invisible until we developed the tools to see it, and those tools are improving rapidly. The Vera Rubin Observatory, currently under construction in Chile, will survey the entire visible sky every few nights once it becomes operational. It will detect moving objects with unprecedented efficiency. Current estimates suggest it might find dozens of interstellar visitors every year, might transform these rare encounters into regular occurrences, might provide enough examples to move from case studies to statistical analysis, from anecdotes to datasets large enough to reveal patterns and test theories. Within your lifetime, perhaps within the next decade, the discovery of an interstellar visitor might become almost routine, no longer headline news, but rather a regular occurrence that generates brief interest among specialists, before attention moves on to the next object, the next opportunity for study. But even when they become common, even when we have catalogued hundreds or thousands of interstellar visitors, measured their compositions and trajectories, classified them into types and categories, there will remain something profound about each encounter, something worth pausing to appreciate, even in the midst of routine observation and analysis, because each one represents a connection across the light years, a physical manifestation of processes occurring around other stars, a sample of materials formed under conditions we cannot directly observe. Each one carries within its composition and structure information about somewhere else, somewhere we cannot visit, somewhere that nonetheless becomes knowable, through the patient application of physics and chemistry, to the light these objects reflect and emit. 3i Atlas will continue its journey long after human attention has moved on to newer discoveries and different questions. It will pass beyond Saturn's orbit, beyond the Kuiper belt where Pluto and countless other icy bodies orbit, in the cold darkness beyond Neptune. It will cross the heliopause, that boundary where the solar wind gives way to the interstellar medium, becoming once again an object defined by galactic space rather than solar influence. Centuries from now, millennia from now, it will drift through regions of the galaxy we cannot predict. We'll pass near stars whose names we do not know. We'll continue the journey it began millions, or billions, of years ago, when some gravitational perturbation ejected it from the only system it had known. Perhaps it will eventually be captured by another star's gravity. We'll become part of a new planetary system. We'll join a new family of comets and asteroids and planets, orbiting a sun that is not the one that warmed the materials from which it formed. Perhaps it will wander forever, never captured, never finding a new home, simply travelling through the galaxy until the universe itself grows old and cold, and even stars no longer shine. We cannot know its ultimate fate, any more than we can know its origin. Both ends of its story remain hidden beyond the horizon of what we can calculate or observe. We know only this brief middle section, these few months when 3i Atlas passed through our solar system and graced our instruments with its presence, when we could observe and measure and analyse and wonder at what this visitor might teach us about the broader universe we inhabit. We have wandered through this story together for a while now, have drifted through discovery and analysis, through chemistry and physics, through encounters and searches for origins, through lessons and implications. The journey with 3i Atlas has been gentle, contemplative, a slow exploration rather than a rushed sprint toward conclusions. The question remains, and perhaps will always remain. Where did it come from? Which star was its parent? What planetary system gave it birth? We do not have final answers. Perhaps that is fitting. Perhaps the questions themselves are what matter. The ongoing search for understanding, the patient accumulation of observations and analyses, that constrain possibilities even when they do not provide definitive solutions. For now, let this thought sit with you, as you drift towards sleep, as consciousness releases its grip on details and facts, and surrenders to the less structured realm of rest and dream. The universe is vast, far vaster than human minds can fully grasp, but we are part of it, connected to everything else, through chains of causation and exchange that span light years and eons. 3i Atlas reminded us of this connection, carried evidence of it, frozen in its ancient ice, demonstrated through its very existence. That stellar systems are not isolated islands, but participants in larger galactic processes. We do not have all the answers. We never will. But we have questions, refined through observation and analysis, into forms that might someday yield to further study. We have data, carefully gathered and preserved, that future astronomers with better tools and deeper understanding might revisit and extract new meanings from. We have the memory of this encounter, this brief intersection of human capability and cosmic wandering, that allowed us to study something genuinely alien, genuinely from beyond our solar system's boundaries. Thank you for wandering through this cosmic journey with me tonight, for letting these thoughts about ice and chemistry and the vast distances between stars accompany you toward rest, wherever you are in the world, whatever darkness or light surrounds you, whatever thoughts and concerns occupied your mind before you began listening. I hope this gentle exploration has brought some measure of peace, some appreciation for the universe's quiet wonders, some recognition that we live in times when questions that previous generations could only speculate about now become answerable through patience and careful observation. The universe will still be here tomorrow, still vast, still mysterious, still offering questions for curious minds to pursue. 3i Atlas will still be travelling outward, growing fainter, but no less real, carrying its secrets back into the interstellar dark, and somewhere, perhaps, another visitor is already approaching, another wanderer from beyond. That will eventually cross our detection threshold and offer new opportunities for observation and wonder. For now, rest. Let the details fade, let the questions remain unresolved, without that causing any concern. Let the vastness of space and time become not overwhelming, but comforting, a reminder that existence extends far beyond our immediate concerns, that we participate in something larger than ourselves, something ancient and ongoing that will continue long after we're gone. Wherever you are, I hope you find rest.